E, because the hypercosine and those things can be put together. So exponential hypersine mu x sine mu x plus f hypercosine mu x cosine mu x plus g hypercosine hypersine mu x cosine mu x plus h hypercosine mu x sine mu x. Okay, hypersine with cosine mu x, cosine hypercosine, cosine mu x. Okay. For fourth root solution, that's why in the textbook or some paper, they directly write out something like this. Sometimes confusing. Why? Okay, that's why. Understand? Ali, okay?
I just confused the...
This one? Yeah. So you have a C1, okay? You put the C1 with this one, right? C2. C1 cosine with this, right? So that will be, E will be sometime like C1 plus C2 something. Okay, right down here. So you have C1, okay, hypersine mu x plus hypercosine mu x with a C1 cosine mu x plus C2 sine mu x. Because hypersine x is equal to half exponential x minus x minus, and hypercosine x equal to half x plus minus x. Okay, this definition for hypersine, hypercosine. Then from here, this equation will equal to plus hypercosine mu x minus hypersine mu x times C3 cosine mu x plus C4 sine mu x. Okay, so this will equal to, for the hypersine mu x sine mu x, hypersine with sine mu as a C2, right? Plus hypersine mu x minus C2. So this C2 minus C4 plus hypersine cosine hypercosine mu x times cosine mu x. Hypercosine with cosine mu as C1. hypercosine cosine is a C3, right? So will be C2 plus C3. Similar, we have hypersine mu x cosine mu x. Hypersine cosine. Hypersine cosine C1 minus C3. Plus hypercosine mu x sine mu x. It will be hypercosine sine. Hypercosine sine C2. Hypercosine sine C4. C2 plus C4. Okay? Then I define this is H. This is G. And this is F. This is E. Okay? All are constant to be determined. Okay? But for different function with different coefficients. And those coefficients are determined by boundary conditions. Later, okay? After you add particular solution, then you determine, okay? Don't write immediately after you solve the homogeneous solution and you determine the coefficient. No, you should combine with the particular solution and boundary condition, okay? Yeah. All right. So the hypersine x is look like this, something like this. Maybe not. I don't know. So that's why. Okay. And hypercosine x, okay, and this is x, that will be equal to 1. And the derivative hypersine x is just like the derivative of half exponential x minus exponential minus x is equal to half ex plus half e minus x is equal to hypercosine x. And the derivative of hypersine cosine x equal to d dx half plus e minus is equal to half ex minus half e minus x is equal to hyper sine x. Okay? So you can see the derivative of this one is the slope getting 0, okay? From positive to it's a positive getting to a constant slope, then increase slopes, just like this. So the derivative of this will be cosine. So the slope will change in and to here, the slope equal to 1. then increase again. The slope increase again. Okay, the slope decrease to 1, then increase. So derivative of sine, hypersine is hypercosine. Derivative of cosine, the slope is negative. Negative, negative, negative to 0. And plus. So there's a negative value slope and to 0 slope. Then plus. Okay? Derivative. All right. That's the homogeneous solution. So far, okay? Did you learn before? Sorry. No. Okay. Understand, right? Can you understand? Okay. Anyway. So that's the first time you learn it, okay? Okay. All right, so after we got the homogeneous solution, then let's solve a problem. Okay. Let's see an example. It's a beam of a finite length